Jaafar, VP of Marketing, Digital Com and Application Lab from Dolphin Design. Welcome, Hakim. I hope that you solved your issue about the network. Can you hear me?
Yeah, I can hear you.
Oh, great to have you. Welcome to this session, and happy to see Dolphin with us this year. Hakim, we are going, means you will go through the embedded, and I think it's good thing that we end with this session. Hakim proposed to go through all the standards, at least to the embedded security through use cases and associated standards, means he will give us this workaround, let's say this, and let's have this, and then we will have our roundtable. Hakim, the stage is yours. Please introduce yourself, introduce your company, and start your presentation.
Thank you. Can you see my screen?
Yeah, very well.
Perfect. Thank you. So hi everyone. My name is Hakim Jaafar. I'm VP Marketing at Dolphin Design. My background is mainly semiconductor guys since 23 years, with a career in the technical side, test engineering, the application engineer, and then I moved to the marketing side, mainly working for a company named ST. And now I'm driving the roadmap of Dolphin Design. So Dolphin Design is a company that is designing IPs for semiconductor industry, microcontroller, MPUs. We design many blocks. We also provide IPs for AI, computer vision, DSP, power management, audio as well, audio and high quality audio, MCUs, a lot of IP, everything that you may need, in fact, to tailor your device. So let me start quickly the presentation, which is about the use cases, mainly around the security. So a quick agenda around 4 steps: the use cases, the security IoT landscape, the kind of embedded security you may need or see, and the certification program. And we'll go quickly through a takeaway. So actually today, there is a deluge of device to be secure or not. Security is good, but it's not always mandatory. If I have a look at different segments, like the industrial one, I see application like, metering, street lighting, smart agriculture, smart industry. We can go for personal equipment, IP camera, fitness watch and trackers, asset trackers like bike, home door lock, white goods. And on the healthcare side, you have all the insulin pump, glucose monitoring, and so on. All those IP now tend to be secured. Why? Because they are connected most of the time wirelessly. So the wireless device, we can say they suffer from physical attack. I have a wired device, the wired one suffer from physical attack because I have to go there, access to the device to hack it. While the wireless one, they suffer more about remote attack. So I can attack them remotely, physically as well, but also remotely. And that's why actually there are more and more IP, whatever, hardware and software that are built to protect against the cloning. The worst would be to clone a device. You can kill a device, you can make it not functioning correctly, but the worst is to clone it, and therefore you are inside the network, and then you can hack the entire network. And there are other also, I would say the way is to make the radio protocol much more secure. If you take a Bluetooth device or Wi-Fi device, you can secure the device itself, but you can also secure the protocol itself, like the Wi-Fi, the BLE. Even if they are natively secured, we'll see it later on, you can increase this security. So the first question we may have is, what am I trying to protect here? We're talking about security, and I face many customers say, hey, I want a secure device. The question is, what do you want to do exactly? What are you trying to protect? This is the real question. I can have some different use cases. For instance, let's take the example of a temperature sensor. For the temperature sensor, what I just want to know is the temperature, right? I want to make sure that I get the temperature from the right sensor. And in some extent, I don't care even if my neighbor got the temperature of my kitchen, right? I don't care if you know that at home it's 22 degrees C. But myself, I want to make sure that it is this perfect device, which is mine, that is talking to me. This is called authentication. You have other use case, which is, for instance, a free Wi-Fi access. On this one, what you want to make sure is you don't care who is connecting, but as soon as you connect, you want to make sure that your data are private. And this is privacy. You see, so we start distinguish here two use cases. One is authentication, where who is talking to me is more important than the security of the data itself, right? And the other side is the security of the data. I want to make sure that no one can get those data, but I don't care who is in my network. And then you have the combination of both, like when you pair a device to your smartphone, for instance, a headset or smartphone. Here you care that both devices recognize themselves, both devices can talk to themselves in a secure way, and that the data are private. And this is, to me, what I call security. So it englobes authentication and privacy. And just to know more what it's about, the authentication is just to verify the users of the system identity. You don't care about who can get this data. Privacy is to ensure the personal data, right? Ensure the personal data are secured and given only to the authorized people. And then the security is to protect against authentication hacking or privacy hacking. Now, this being said, there are different examples of attacks. Let's have a look first with the physical attack. I list many of them here, which are the most known of them. We have power analysis, which is clearly measuring the power consumption of the device with an analysis, and to know when you execute this function, what are the blocks that are powered. And this is useful sometimes to hack a device, to get some keys or something like this. You have the electromagnetic analysis, same way analysis, in fact, which capture the electromagnetic radiation. You have the timing analysis, very interesting when you have, for instance, a multi-area device, like you have 2 cores, 2 CPU, or a smart engine running, and you analyze the timing between one action and the response. And you have the injection fault, which is actually consists in injecting errors on purpose in order to see how the system behaves. You have some glitching, which is mainly used sometimes to remove some protection, like memory protection and some stuff like this. Glitching is used for this. And you have the row hammer, which in fact it's repeatedly access adjacent memory rows to see how it behaves. All those attacks will help you to have a mapping of how the device behaves, and then you can, for some extent, for instance, try to understand where is stored the secret key, or and sometimes to get the content of the key as well. Or you can remove some readout protection of a memory and then go there and get the code and access to the software IP, for instance. See, so this is for the physical attack. Now, this is when I can get access to the device, but sometimes the device, you cannot access it easily. It is in a metal box. If you take the example of an antenna, it's high on the roof. So then you have some remote attack. Remote attack can be divided in 2 categories. The software-based one, like buffer overflow, like code injection. So you inject a wrong code when you do an update over the air. You inject on purpose a wrong code that's gonna open the door or shut down the device. The backdoor, right? There are many software that has suffered from backdoor, so it's also a way to hack a device. And there are other attacks which are network-based device. We all know the denial of services, the DDoS. It's one of the most known attack. In fact, you bump a server or whatever with tons of requests in a way that the server cannot answer anymore. It's just going to shut off or in protection mode. You have man in the middle. Man in the middle actually consists in hearing the signal and be capable to repeat it. But then after a time that you are in the middle, you can, if the device uses always the same key, you can rebuild this key, and then later on, in fact, to decrypt the initial message, right? And this is called man in the middle. It was one of the attacks that was well known for. It is, by the way, still in BLE and Wi-Fi, but now there are countermeasures that are put in place to avoid this. And there is the replay attack. The replay attack is, for instance, it was one of the topics we covered when I was in the LoRaWAN Alliance. One of the thread was the relay attack. because you send a signal to the network, turn on the street light, and when you want to turn off, someone said, okay, turn on again, right? And there are some countermeasure here, which is just to add a counter in the message, right? And then the network, when he get the message, he said, okay, I get this message, but the counter is not the same, right? Because you can just repeat the message as is, but if you have something that in the message is changing regularly, then you cannot just repeat it as is, right? And then it prevents against this kind of hacking. So now we see a physical attack, remote attack, and when we said remote, of course, we talk about wireless. Wireless is IoT, and then here the idea is to have an overview of the kind of IoT protocol that we all know, the major one. Tons of other exist, of course, and to see what is the native security on those protocols. We can take the example of the Wi-Fi. Wi-Fi used to go with web protocol, which is outdated now. Now the last one is WPA3 for personal use, which is use an AES 128-bit encryption. But then you have the WPA Enterprise. This one is a bit more robust. Actually, it's an AES 192 based on the AES 256 scheme, plus the HHA 384 bit, right? So those are the encryption used. You have the Bluetooth, right? Uses E0 for the classical and the AES for the BLE. All those encryption are embedded in the protocol, right? So here you have two choices. You can rely on an hardware engine in your device, or you can do it by software, because AES is a computing, right? You can do it by hardware or by software. I mentioned as well Zigbee, which is an AES 128. The ultra-wideband, actually, also it's a 128 or 256, and the LoRa one is AES 128. Those are the native security embedded in the protocol. It doesn't mean that you can add something on top of it, right? This is just for the radio protocol. Of course, your application layer that sits on top of the protocol can also have its own security, right? And if we now have a look at, okay, I have a software protocol. I know this one has an embedded secure software protocol, but what can I do more? What can I add in my device also to make it more secure? Again, same, it depends what you want to do. But with the rise of connected device, attacking a device become much more easier, unfortunately, right? The number of hackers increases, and hacking a device, unfortunately, the solution to hack a device become easier to access. And so to fight back, industry comes with some solution. Hardware block, of course, there are software solutions, but hardware also exists. And here we want to go through some of example. I can take the example of the secure enclave, right? It has many names, called also crypto island, if you talk with ARM, for instance, ARM branding. So the secure enclave is what? Is an area which is completely isolated, where I can stock some keys, or I can stock some AES encryption engine that's going to use the key. It is completely isolated from the system. That's why they call it also crypto island. It's completely independent from the rest of the system, but the rest of the system is going to ask services to the secure enclave, and the secure enclave will just reply with an answer, right? So this is one way to do it. So for instance, you may say, okay, I want to encrypt data. The software to encrypt is free. It's in the flash. It's open. I don't care. But the key that I am using to encrypt the data is in the secure enclave. You have another way, which is the trust zone, which is well used actually in the embedded MCU 32-bit environment. For this, you need to use an ARM core, which is M23, 33, and other generation that comes after the M33. The idea here is to split the entire MCU or the entire platform, whatever flash or IP, in two areas. Secured, the one on the left side, which are blue, and the unsecured, the one on the right side, which are gray. And inside those two areas, you can have subdivisions. So you can have privilege and unprivileged. The idea is to say that my IP, the software that I developed, the software on which I put patent on it, this one's going to be in the secure area, privilege one. Why? Because this one has the authority on all the other environment. The secure privilege has authority on the unprivileged, on the unsecure privilege and privilege, right? And so, for instance, if you go with an open source, you go for Bluetooth, for instance, you say, okay, I'm taking this stack open source. I don't have time or engineer to develop. I take the Bluetooth open source. I want to go fast. The open source is going to be stored on the unsecure side, right? Why? Because it's open. You have no idea of what's inside exactly this Bluetooth stack, if there are malware inside or whatever, right? Like the code injection with OpenSUSE. So this one, you're going to put it in the unsecure environment, right? Because if you put it in the secure, then you can get access to the entire device, right? So it may be strange at the beginning, but think about it. Something that you don't know what it does exactly has to be put in the unsecure side. So Trust Zone helps you to split and to create an isolation. But you still have one CPU, right? So you isolate the task. That's it. Then you have the secure element. To me, is the best-in-class security. So it's an external device, right? But it's made to be resistant over tamper, fault injections, physical attack, and so on and so on. Usually it has a cost because it's an external device, but usually it's what is used in the banking, ID document, and so on and so on. Secure element for today is what shows the state-of-the-art security robustness. And you have a fourth solution, which is dual-core CPU. For instance, you may say that, okay, I'm going to create an isolation where I will have a dedicated CPU, a dedicated bit of flash, and some peripheral as well. And somehow the dual-core is like the secure enclave, like the first one, you see? So you take a second CPU, right, that you're going to isolate. So you create a kind of a crypto island as well. The difference is here, you can have real-time operation. It combines the benefit of the secure enclave and the trust zone, right? Because you can still have this split of CPU1, CPU2, secure, unsecure. But the thing is, because you have two CPU, you can go for real-time operation. In the industry, sometimes you may have some CPU controlling some engine rolling and stuff like this. Is critical. You need a real-time CPU dedicated on this, and another CPU to run the human interface machine or whatever. Sometimes you need to have real-time, and so two CPUs. So those four typology exist today, and each one of them have their pros and cons for sure, but they are topologies that exist and solve many, many issues. Now, we may say, okay, we have the device, we know there are attacks, we know how we could protect against them, physical, the software protocol, but at the end, how do I know that I am secure? How can I quantify it? How can I justify it when I say I sell a device to a customer? How can I say, okay, this is securely at this level? For this, there are standards, right? The good thing of standards is they give a common calibration to everyone. In the embedded world, there are two standards today. There are many, but two of them are very strong. One is PSA. Why? It's a platform security architect made by ARM, right? So every time you want to embed the trust zone in your device and you want to show how it is secured, you can go through the PSA certification. And you have also the CZIP, which is a derivative from the common criteria. CZIP has been a derivative to address the IoT industry. It's a simplified version. It doesn't mean it analyzes less security. No, it's because common criteria englobe a lot of applications, a lot of schemes of security. And globally, it's like this. I try to summarize it, but globally, if you go through three level, level one usually is self-declaration, right? You have a memory without protection, you have some AES 28-bit hardware encryption engine, and you say, okay, based on what I have on my device, I said that I can match level one. For instance, in PSA or CZIP, it's auto-declarative. Level two is to protect against certain kind of attack, which are software and some light hardware attacks. And the level three is, here you are much more robust. It's so for level 3, you have to understand that the entire microcontroller, for instance, or device could be CZIP level 3, for instance, or just a part. So you can just say, okay, my crypto enclave is CZIP level 3. And this here is much more stronger. You can justify of a root of trust. You can have a secure engine, which is robust to hardware attack, to side channel attack, and so on and so on. You see? Just to note that CZIP can go up to level 5 actually. But for MCU and embedded microcontroller, usually we try to align them with PSA, and to show the 3 levels, just to give you a quick overview on this. So we saw the application, the kind of security and hacking that could happen, how we could prevent them, how I can justify my security and what level of security I put in place. And here I'd like to end up with a takeaway on all this quick overview. Security is a vast topic, right? Security is a super vast topic, and you really want to know where you're going, what do you want to secure. And before starting, you have to define exactly what you want to do, right? It's really important. Otherwise, you're going to use a bazooka to kill a mosquito. And security, you understand, is like a pipe, right? From the end device to the cloud, for instance. So if in this pipe you have one leakage, it means the entire platform can be unsecured. And keep in mind that the level of security is equal to the weakness link of the system. Whatever you do, if you have one weakness link, this is the level of security you can achieve. I remember in the past, I saw super Wi-Fi device, super encrypted, super microcontroller, super encrypted, both two devices connected with a UART in between, and the data were set in clear in between. Therefore, all the security is pointless for a physical attacker. And to illustrate this, I just picked up for fun 3 pictures that illustrate to me sometimes a kind of security. So for the first one on the left, indeed, there is a gate, but it's useless. I like very much the one on the middle. There is a big chain and everything, and the hard lock, but there is this tiny plastic that keeps everything. And for the third one on the right, actually, there is just a wall. So sometimes you just don't need to have a security. I'd like to thank you for this. I hope it was...
Thank you so much, Hakim. Thank you for this great presentation. And I think it's good to give this overview where you span all the use cases almost and the challenges. Now I have a question. At the end of your presentation, you mentioned it. You need to know exactly what you have to define. As entrepreneur, for example, I'm building a product. All what I need, I don't have problem. You see, I'm not an expert in security, and all what entrepreneurs need, people that building new products for IoT or for any, they don't want to have problem. This is all what they need. Means they are not expert. They know that is an important issue to handle, but they don't want to handle the complexity of such kind of technology because it's very complex. All the solutions, how to select. Please tell us what is the way for an entrepreneur building a new product, what is the best way to select what the technology or to make sure that she or he will not have problems.
So I'm sorry, I just turned off my camera because I think I have some issue of bandwidth.
No problem.
To answer the question, first of all, I will strongly advise to make sure that when you design your services, whatever, make sure that all the bricks fit with a certain level of security. First of all, make sure of this. And then also, I will strongly advise that there are companies that you can pay to make an audit of your system before rolling out any end product, any services. Pay for this audit because it's not super expensive, and at least you can have a feedback and people advising you, hey, look, you have some breach here, and there. Because sometimes we don't want to fix a breach. Oh, come on, it's not so bad, but the financial impact can be big. So my advice would be select players that can show a certification or that can help you reach a certification. And then once finished, go for an audit, an external audit, even if you have to pay it, but make sure that your system is secured.
Okay, means rely on certification, follow players that have been certified to make your choice. Okay, let me just look look at the chat. Yeah. The next question that I have is about root of trust versus a blockchain. What do you think about? Because you presented the use cases, but many entrepreneurs are now saying, okay, you have this root of trust approach that we see this morning with Secure IC already put it in place and approved by the Security Act or the Cyber Security Act. Means there is a lot of, in Europe at least, a standard around it. But we have also blockchain is Web3, is decentralized. It looks the new technology that we should rely on. How do you see this dual between those root of trust security and the blockchain?
So it's a good question. The root of trust, actually, when you want to justify that you have a root of trust, the definition is I have an immutable way how my product starts and is secure. So from the time I power it up, so while I put the battery till it is ready, the root of trust is how this is immutable. Then there are different ways to do this. Blockchain could be a way how you achieve this, right? But in the physical environment, for instance, you said, okay, I wake up, this CPU and this CPU connect to this and that and then that, and this is immutable. So whatever you play, you shake the device, this will never change. Now, the blockchain can, for instance, help to, when you boot up, to validate that part of the code you are executing, for instance, is the trust one. So I see the blockchain as a complementary, right? Complementary, yeah, to the root of trust.
Means whatever, even in a decentralized web, in a blockchain everywhere for data, and blockchain everywhere for IoT, and blockchain everywhere, we will always need root of trust to make sure about the device itself. And blockchain is more in the transactions. This is how.
Correct.
Okay, thank you. This is this is clear. My next question also about this global approach. I mean, how to have a global approach. Here again, I'm back to what we saw this morning. How we have this global security approach when you have China with their approach and trying to protect, of course, themselves with their own standard, Europe with their own standard, North America with their own standard. Means how we have such security interoperability in place globally. If I sell a device to China, how to make sure that I will be aware about what's happening, and I can, of course, make alerts or make something.
Yeah, it's a very good question, because we see this with the decoupling of the economy. We see exactly what you said. Every, we said, regions of the world, they want to go for their own security. And most of the time they look almost the same, but they have some differences. I'm thinking about AES, about HSA. Unfortunately, I think there are bridge between standards that exist. I'm thinking about, for instance, Matter protocol, about LoRa 1. There are some bridge that exist between a European or European American and China. So this is a good way to make sure that your device can support this, be part of this bridge initiative. And for the physical, I would say, the hardware device, the hardware encryption engine, for instance, unfortunately, you will not have the choice than support both of them if you want to have a device that can go everywhere.
This is thank you. Thank you for answering to this question, because I think this is also the point. We need to be resilient with also the fact that we will have different security approaches. I mean, different security for political reason, by the way, as you mentioned it. Thank you. Let's finish with Dolphin. I have a lot of respect for this company. And I'm happy today to have you. Can you tell us more about Dolphin? What is your next challenge? What is your positioning in this security and your next challenge? We don't hear you anymore, Hakim.
Sorry, my bad. So for the security, the way we're going with Dolphin Design is we do have what we call this an MCU backbone or an MCU subsystem. We try to help companies rolling fast a solution on the market, and because it's an industrial trend, the security is there. So we are offering a platform that can support different architecture, dual core architecture, can support also a crypto island, a trust zone, and so on, or a secure element. So our way is to say security there, it's a trend, and we take our MCU platform and we just augment it to support the 4 various cases I showed previously, whatever ARM-based, RISC-V based, or whatever.
Yeah, you adapt yourself to the customer request.
Correct. And
yeah,
to the market.
You are more focusing on customizing solutions to your customer,
Exactly.
what is coherent with your positioning and strategy. Hakim, thank you so much. I was happy to have you. Have you tried to contact the other speakers and discuss with them? I know that Pranesh sent an email. Have you had the opportunity to organize meetings with the other speakers?
I saw the email. I have to reply to it, but I need to spend more time to talk to the others. I saw the email, and I will definitely reply to
them. It makes sense because I think with Dr. Sumia Benraji, we'll have, Trasna is also safe IoT, means I think they will require a lot of things to exchange with Dolphin. And the other speakers in India and also in France, it makes sense that we take really the opportunity to discuss more about it. Thank you, Hakim. Thank you for all my speakers. I will end this session here. I think we went through a lot of discussion. Thank you for Secure IC. It was great, to see their presentation today and to see how much they progressed. They worked hard. I know them since 10 years. They worked hard to have this cybersecurity, this CHIP Act in Europe, and they are part of this move. I was really happy to see this morning. Thank you for Dr. Banerjee and Trasna, and we learned today about PAF and blockchain and the introduction of blockchain to embedded. Thank you for also our colleagues in India and also to Hakim, who ended this session. Thank you so much, and let's have our next event in 2 weeks about IA. Thank you. Bye-bye.